Now, what we're going to look at today is what happens when we have a sum of forces or a resultant force acting on an object that is time dependent. So, what do we mean by this? Well, consider this example. So we have a point, and acting on this point are several forces represented by vectors. This point has mass m. And of course, the resultant force is, this is our resultant, it's the sum from I equals 1 to capital N of each individual force vector. And if these things were time dependent, which could happen, so in other words, the magnitude of the force and the direction of the force changes with time, then what we would have is, in fact, this here, these would be time dependent. And so the resultant force F that we'd use in Newton's second law would be a time dependent vector. Okay, so this would be a time dependent vector. And this is okay. And we should know how to deal with this, because when we come to Newton's equation of motion, what we have is m, or let's put the time-dependent resultant vector. This is our resultant vector, resultant force. So we'd have this equals m dv by dt. And of course, this, in order to determine v, we just have to consider something like this. Integrating the ratio of the force vector divided by the scalar m with respect to t. Okay, and this is how you tackle this problem. So let's have a look at an example where we'd actually use something similar. So this example refers to a train of mass m kilograms traveling in a straight line. So as soon as you see straight line, you know we're working in the framework of 1D motion. Okay. And this is against a constant resistive frictional force. So there's a frictional force that resists the motion, R. It has magnitude R newtons, and the engine supplies a thrust. Okay, the engine supplies a thrust, and this is a forward force, which is opposes the resistive force, and this is given by this expression when t is less than a over b, and it's noted that a is greater than r, the magnitude of the resistive force. And after t equals a over b, the force is 0, this forward force. So we have 0 when t is greater than or equal to a over b. Right. So we're asked, what is the greatest speed achieved by the train? How far does it travel before coming to a rest? And how long does it travel before coming to a rest? So, don't forget, it's hidden in here, the initial condition. The train starts from rest. So let's draw a scenario. So let t equals 0 be the case when the train is at rest, i.e. v, we'll say v of t equals 0 I plus 0j plus 0k. Now, in a moment, I'm going to delete the vectors we don't want, because it's some of these vectors, some of these basis vectors are not necessary. The unit vectors j and k, you'll see, will just go out. So this is our 1D motion. Draw a train, or try my best to draw a train. There we go. That's as good as it gets. I think these are meant to be carriages anyway. So it is going forward, this train, with a forward force. Remember the cyclist who had a fast sprint, which they did so by having some sort of forward force, which goes with the motion. So the motion is this way. And let's draw our vector on. So this is the forward force, or the thrust. And opposing this is the resistive frictional force, R. Frictional force. Magnitude. Not mg. Magnitude, R. So this axis is on the bottom is the x-axis, and we assume that the train is at 0. We assume, for our sakes, simplicity in calculations, train is at 0 when t equals 0. And this is when v of t equals 0 I. Plus 0j plus 0k. Now, clearly, our train moves in x direction. No other direction. In positive x direction. Therefore, there's no need for J's and K's. Okay, so I'm going to delete them now. Really, there's no need for them. We're just considering 1D motion. So there we go. They're gone. There we go. And you know what? I'm also going to take this out the equation, this y-axis, because really it's just unnecessary. So our forward force, let it be F T. So the forward force due to the thrust. So now, this is our axes. Let me probably draw this in a red pen. Okay. This is 0. So let us now think about the force, the vectors representing the forces. So force due to thrust. Well, this is Ft, and it's defined in 2 parts so that it gives us a continuous piecewise function. So initially, in the first chunk of time, it's defined by this expression a minus this linear function of time for t less than a over b. Then for t greater than a over b, it is 0. Okay. And we note that a is greater than the magnitude of r. Okay. So, what else? Well, here, what you'll notice is in this time interval, this function here, this function is positive. Okay, and it's 0 when t equals a over b. So, just keep this in mind. Okay, so this is definitely this is our forward force. I've wrote a vector, by the way. It's a bit naughty that I haven't done what I usually do. So let's just make this a vector. So it's like this. So the i's represent the unit vectors in the x direction, And of course, they're positive. They point in the positive point in positive x direction. Okay. So, what else? So we have a force due to friction, and we'll call this R. And it basically has a magnitude R, and then because it acts in the x direction, you should use the basis vector I. And following this, what we should do is we should tune the sign so that it corresponds to how it acts in this diagram up above. And in fact, so this points in the negative x direction according to our diagram, so we need minus in front. Okay, good. So last step, Newton's equation of motion is the following. F of t equals m dv by dt. Okay. F of t, excuse me. By the way, let's change some notations. Remember that F of t is the resultant force. So Ft, this should be Ft here. So F of t is formed from just summing the forces applied to the train. Okay, and if I add these together, it gives me the following. So I'm going to go to a new page now that we have everything that we need. I'm going to take this. Okay, and we're going to write the resultant force vector. Okay, there we go. Right. Okay, so what is F of t? Well, clearly this is the following. Using the definition of Ft, we have and the definition of R, we have the following function. So it's A minus Bt minus R I for t less than A over B. And it's minus Ri if you just add these two functions together and consider these two time intervals for t greater than A over B. Okay, so basically let's draw Ft. So Ft, Ft is the following. Ft I, where Ft is a scalar function that is piecewise defined. We don't need I because it's not a vector, so it's like this. And if I plot this, this is what the forward thrust looks like, or the magnitude of the forward thrust. This is Ft, this is t, this is 0, time t equals 0. So of course, here we have, there's some positive force at the beginning, there's some magnitude of A for the forward force, and then at time t equals A over B, of course this thing's 0. So I have a straight line with negative gradient. So I have this. By the way, we're assuming that A is positive, B is positive. And then afterwards, it's just 0. Okay, so that's our function. Then what about capital F? Well, it's just the vector capital F. What about its magnitude? So the vector capital F is like this. Oh, and by the way, it's probably useful to just say that R is greater than 0. R is the magnitude of the vector R. Now, here what we have is F of t is defined by another scalar function multiplied by I, if you look at this. And f of t is, of course, this function now. A minus bt minus r and minus r. So in effect, this is some shifted function. It's the same graph, but now it's shifted downwards. So if I draw the graph of our resultant force, this is T, this is F, this is 0. Let me grab the pen. So the right pen, A. So A is greater than R. So when T is 0, we start initially at A minus R. And then we come all the way down to A over B, where we hit minus R, and then it remains at minus R. So that's our magnitude of the, or if you will, this is the, this is the force vector applied. This is the force applied to our train. All right, so what have we got to do? So we can do two things. So right now, what we've got is the following equation. So we can introduce this. V equals V of t, I. Let's also introduce F as we did before, F of t, I. So this gives us the equation, the m dv of t I equals f of t I. And this just gives us the following equation to solve. Now, we've solved similar equations to this when we started looking at modelling with first order differential equations. So we have this. Remember, the vectors are only equal if the components are equal. So if we think about f, then of course this is a minus b. Let me just rearrange some terms. A minus r minus bt for t less than a over b. And this is minus r for t greater than a over b. So because we solve similar problems, what we're then going to do is we're going to look for a function v split in the following form. So v of t will be v1 of t, which takes care of the first time interval, and v2 of t, which takes care of the second time interval. Okay, so in this case, if I combine this information, so let's take this information to the next page. Okay, what we have is our equations are so V1 is responsible for the first time interval. Good. Equals a minus r minus bt. And this is for t. And then you have the second function satisfies this. Okay. So now it's up to us to really just find out what the velocity is and the position vector, etc. So let's do this. Actually, what I'm going to do is I'm going to split the analysis into two cases. Case 1. And this is something separate from what we said above. So train may stop in interval 0 t a over b. Okay, 0 to a over b. Right, okay, in this case, so that's 1, 2. So in this case, there's no need 4, 2. All right. Okay. By the way, I think, have I... Okay. Okie doke. So, good. Now, what does it mean that the train stops? Train stops when the velocity is 0. When velocity v1 of t is 0. Okay, we know that actually v1, we have a condition on this. v1 of 0 is 0 because the train starts from rest. We have x1. What's x1? Well, x1 is the integral of v1. Better to write this. Well, we have a condition on the initial position, x1 of the train. So x1 of 0 is this, where this is how v1 is related to x1. Okay, so we're ready really to start solving the problem. So if I take a look at C1, what have we got? We have dv1 by dt equals a minus r over m minus bt over m. All right. And what I need to do is I just need to integrate with respect to t. So I get v1 of t equals integral a minus r over m minus bt over m dt. And of course, if you do if you grind out the integrals, this is what you get. Minus bt square over 2m plus a constant. Let's put c now. So this is an arbitrary constant of integration. Const of integration, int. And we can get this easily because v1 of 0 is 0. So this implies that we have 0 equals v1 of 0. And if I use our expression, we simply have a minus r over m times 0 minus b times 0 square over 2m plus c equals this. So this just implies c equals 0. So therefore our v of t, so this was initial condition, our v of t gives us, now this is what it is, our v of t is this. Okay, so notice that this is a quadratic in time. So I can write this like this. Okay, and remember that when t equals 0, so when v1, according to this, of t equals 0, we have this equals 0. So this implies t equals 0, which is when train starts, or what? T equals 2a minus r, just by looking at this factor, 2a minus r over b. Now, I've said, so effectively, what we're looking at is when the train stops in the interval from 0 to a over b. So if I just draw this parabola, note that this is a convex parabola, okay? So it has a maximum. So if I just draw this is our v, v1. This is t. This is A over B. This is 0. So there is a parabola and we need a condition. Looks something like this. This is our 2a minus r times 2a minus r over b. So clearly here we have a max speed. And there's another condition. There is another condition which corresponds to when the train stops before t equals a over b. Okay? So effectively, so for instance, for this to all work, what we're talking about, we need this. Agree? So how can we find this out? Well, this imposes an inequality on the resistive force. So let me take this across and we'll get all the juicy details related to this now. Okay, so we have this scenario and we would like to know if this is indeed going to stop in the first time interval. We'd like to know inequality on A and R. Okay, so inequality on A and R. So what we'll do is simply subtract one from the other and see when it's less than 0. So of course I want A over B to be greater than the first term. So we do this, sorry, that is not right. Okay, so we do this, subtract one term from the other, and this just gives us the following. This gives us A minus 2R over B. Okay, so if B is greater than 0 and if A is greater than 0, it means this is negative when A is less than twice the magnitude of the resistive force, which implies, A minus 2R is less than 0, which implies A is less than twice the magnitude of the resistive force. So that's the sort of regime we're in. So for the train to stop in this first time period, you have to go against what we initially assumed and we have to add in this condition. Okay, so this was just to give us a feel for playing around with this. Okay, next. So what about the max speed attained? Well, max speed attained clearly comes from looking at when dv1 by dt is 0. Okay, so what about this? Well, don't forget that this was our equation. Okay, this was our equation for dv1 by dt. So this is at time capital T. This is, if I just add this to the diagram, this is capital T. So really now let's update this equation. What we've got is to just put this equals 0 and find capital T. So what you end up with, of course, is T equals A minus R over B. Okay. So this, therefore, remember the A is greater than R, and in this scenario it's less than 2R, so it's in this interval here. So this time is indeed positive. This comes from the start of the question, this condition here, and we also added in the fact that we've got the other condition from what we just found. So this is the time for max speed. Okay, now What about v1 of t? Well, v1 of t is the following. So it's a minus r m capital T minus b t square over 2m. Now, to save on a bit of algebra, what I'm going to do is I'm going to use a power tool to just crank this out. So we have, and you can double check this in your own time. So t equals a minus capital R over b. And I'm going to substitute this in to this expression, a minus r over m times capital T minus b times t square over 2m. So I'm just checking the expression I've entered so that I don't have a problem with this. So if you're doing this, you'll have the following. A minus r over b minus b over 2m, a minus r over b square. Okay, yeah, that seems to be okay. So if you do this, and I'll just simplify, you should be able to verify that the max speed occurs at this time. You get this, r minus a square over 2bm. So that's our max speed. All right, easy one. By the way, we were asked to find distance traveled when train stops. Okay, so for this, well, we know when does the train stop? We found it before. We know at t equals 2a minus r over b, was it? Let's just have a look. Yeah, train stops. Now, recall dx1 by dt equals v1 of t, which will be equal to the following. We found this before, so we just have to integrate. And then all we need to do is find the arbitrary constant with this, which this will just render our arbitrary constant 0. So integrate to find x. Integrate with respect to t to find x1, and use x1 of 0 equals 0 just gives us the following. So these are steps we've always been applying. So this is x1 is then this, a minus r over m t with 2 in the denominator square minus b t cubed over 6 m. And I'm not going to write the arbitrary constant because that constant is just killed by this. But if you check, you can check by throwing this expression into here. These two conditions, they definitely do satisfy the correct conditions imposed on them. Okay, so now what we need, so this is x1 of t. X1 of small t. So let us now find the distance traveled. Distance traveled is x1 of capital T, which just gives us, if you sub this in, you should do the calculation yourself. I said capital T. Of course, capital T was reserved for the time to reach the maximum. So make this T star is T star to m. 2 a minus r over b square. Of course, this now starts to get a bit messy, as you'll probably appreciate, but if you want, okay, you can crank this out again. So let me just see what I get for this. It's not going to be nice, let's put it this way, but let's just see. So I'm going to now put in time taken to stop. Right. Oh, sorry, the distance travelled before it stops. So what have we got? So I'm substituting 2 times a minus capital R over b. Let's just double check that's our time. Yeah, it is. Okay. And then you get this. You can find that this is the following. You can find that this is 2 r, a minus r cubed over 3mb square. Okay, so that's it. So check this. Okay, so that was for a case where train stops before a over b. So next what we'll do is we'll take this, and we'll look at the next part of the question, which is when this thing stops after a over b. Okay. So we already know. So what we know is now we have the following equation. So we know v1 of t, we know. And this is for the case now when train stops for t greater than a over b. So we know v1 of t, that's going to remain the same. Remember, we need a v2 for this second time interval, so I'll grab the equations in a second, but let me just show you what's going on here. So let me just, first of all, I'll grab this. Let's see, did I write this out explicitly? Yeah, these were our equations. Very good. These were 1 and 2 that we never refer to. And here we go. So we have this. So this one's ticked off. We don't need to do anything for this because this holds even in this step. We've done V1. Now we need a V2. Now, V2 is something that we can grab from this equation. Okay? What I'll tell you is happening is if the train stops, okay, if the train stops, this is the speed, this is t. If the train stops after t equals a over b, then what we have is the following graph for the velocity. So you have like last time, where there's a max speed. Of course, you can determine this. We found it before. And then it hits here, and then there's a straight line drop, okay, to rest. And this is covered by V2 with a negative gradient and some intercept. So this is V2 of t. So this will have gradient minus r. Okay, so it's up to us now to solve this problem. So what should we do? Well, first of all, by the way, just put that there, linear here, it's linear. So we have this equation to solve, big deal, because r's a constant now for t is greater than a over b. So this gives us v2 of t equals, now the integral of minus r over m. Now you might be saying, well, why haven't you just integrated? Well, there's a reason for this. There's a reason because I want now functions. I want to see some functions that just vanish. Functions, this is just for ease of calculation. You can do it the long hard way. Vanish when t equals a over b. Therefore, when I integrate this function, what I'm going to do is I'm going to integrate the constant, and it will indeed be multiplied by a linear term, but it won't be just t, it will be t minus a over b, where a over b is a constant, and there'll be some arbitrary constant that I'm interested in. Okay, there's nothing wrong with what we're doing here, so this is C2. Here what you do is find C2 using what? Using the fact that V1 of A over B should equal, let me just write this down. So V1 A over B now should equal V2 A over B. Okay, so they join at this point on the graph. Remember, we've seen similar problems like this before. Fantastic. So, okay, so this gives us the following. This equation gives us the following. I will try not to go into detail on how to calculate this. It's probably straightforward anyway. So, we have the following. Of course, this will be A over B minus A over B using our expression. So obviously this is 0, and this C2 is therefore V1 A over B. Okay, that's the idea. All right then, shall we see what V1 A over B is? Okay, so this is a it's a bit of there's some work to do there, but okay, you can punch this in and I'll give you the answers in a second. So this is what we have. This is our constant C2. Good. So now this implies that V2 of t is minus r over m t minus a over b plus V1 A over B. Okay, now I'm going to find out what V1 A over B is. Okay, so this is in fact our intercept, this V1 A over B on our velocity versus time graph. So we have this, and remember that V1 is the following. I have to trace back and grab this. This is V1. Here we go. So of course we have to copy A over B into this. So it's this with t equals A over B. So let me just again get us this value. So, right, here we go. Okay, tell you what it is now. A over B goes in there. Okay, and this is what we get. So this V1, you should be able to check it's this. This V1 is the following constant. A multiplied by A minus 2R over 2MB. All right. And this makes sense. So in order to stop in this period, remember that A should be greater than 2R, because if it's less than 2R, you're stopping in the first period. So this velocity here, this V1 of A over B is positive in this case. Okay. because of this. Great. Next, what I want to find is x2. So x2 of t is distance or displacement from O. When t equals when t is greater than a over b, greater than or equal to a over b. And this is just linked to v2 as follows. So it's another integration job for us. And of course, to make my calculations, my life easier, what I'll do is I will integrate and introduce factors which vanish when t equals a over b, which is the boundary point for this interval. Okay, so if I integrate with respect to t, what I get is the following. Of course, I'm going to get x2 equals the integral minus Rm t minus a over b plus a minus 2r over 2mb, all integrated with respect to t. Now, this just gives me the following. Again, I'm keeping life easy, so I'm going to keep with factors that vanish when t equals a over b. So I have t minus a over b squared divided by 2 multiplied by minus r over m plus, now this term, t minus a over b. And as you can see, this is a nightmare. But if you have the power tool to do the job, then it's easy to do the simplifications plus c3. Now, this is again constant integration. And you're going to get this how? Well, remember that we dealt with examples in the past where we've got piecewise defined functions. So this one, it comes from C3, comes from matching condition. So matching x1 at a over b with x2 a over b. So therefore, x1 a over b, which I won't write down for now, I'm going to leave that as homework for you, equals, therefore, x1 a over b should equal the value of x2 a over b, which according to our expression is this nightmare of a thing. But actually life is easy because we kept the factors that vanish. Okay, a over b minus a over b plus c3. So c3, remember that this is 0. This is 0 now because we have a over b minus a over b as factors in this. So c3 implies c3 is just our constant, whatever this is. Okay. Fantastic. So then x2 of t is the following. Minus r over 2m t minus a over b square plus a minus 2r 2mb t minus a over b plus x1, whatever this is, a over b. And we know what x1 is. So we can calculate this. I'm not going to do this now. Now, remember, when does it come to rest time? When train comes to rest. For t greater than or equal to a over b gives us the following. So remember that our v2 should be 0 when v2 equals 0. So there is a time t where V2, capital T, put this star star, so when V2 of T star star is equal to 0, and let me just borrow this. Okay. So we need to know when this expression is equal to 0. All right, well, i.e. this. Okay, so this we can solve. I'm going to solve it and then end there. So we want to know when this is equal to 0. So when the train's at rest in the second period. So if I solve this, it just implies that capital T is equal to A over B plus M over R times A minus 2R over 2MB. Okay, of course, there's going to be some cancellation here with the M's. So, again, I'm just going to go to the machine and work this out quickly. So, A over B, right? Okay, yeah. So, if you combine this together, what you get is A squared over 2BR. All right. And then what? So then you go back to x2. So now we know when train stops for t greater than or equal to A over B. What's the distance travelled? Well, I'm going to leave this for you to calculate, but all you need to do is sub t, sorry, that's t star star. T star star equals A squared over 2b r into x2 of t. Okay, and the answer is, and this will give you the distance travelled by the train, and you'll have such a fun time doing this calculation. And what you should end up with is the following. Okay, what you should end up with is here, A cubed. You should end up with 3A minus 4R divided by 24RMB squared. And that's it. Again, so all I can say is have a lot of fun over the Easter break doing this type of question. And I'll see you next time for more on velocity-dependent forces. See you.